All right, chapter 15. Uh, so this is a chapter we're going to talk about polymorphism. Polymorphism is of course, sort of the hallmark, in addition to inheritance of the OOP paradigm. And so what does polymorphism actually mean? And so let's take a look at this. So first of all, you need to understand in order to use polymorphism, you have to actually uh, use either a pointer to a base class or a reference to a base class. Well, of course, because if you don't do that, then you have, if let's say you have uh, a object of a type that's a derived class, and you don't really get polymorphic behavior because you just have a regular object that is you're not really using the polymorphic behavior. So what do I mean by that? So first of all, uh, you got to differentiate between the two things. So for a uh, let's say we have an object that's pointing to a box, let's say the P box here. So you see, this is as you see the declared type in this statement, you have you declare the P box, that's a type of pointer to a box, and that is it's a static type because static in the sense that the compiler will know during the compilation time. And the dynamic type is the type that may be given to it, the actual object, um, the type that will be determined at runtime. So the difference is, let's take a quick look here. We have an object, a serial, and the serial pack is derived from carton and a food container, and then carton is derived from box, right? So this is the class hierarchy on the right hand side. And then so now let's say you have a pointer of pointing to carton, you initialize it with a serial object, and that is fine. Well, because carton is the base class of a serial. So it's okay to have a pointer pointing to uh, the object that's more specific when you declare the type as a carton. Yeah, remember that what we talked about last time is this object contains sort of like a sub-object of carton. This is a base class. So this is not an issue here. Um, and then similarly, you can basically use a pointer to any base class to hold on to an object of a more derived class. Um, so then in the case of, let's say the P box here, and then we'll reassign, we assign another object to it, which is now well, this is the address of carton object. So let's say it used to be in the beginning, initialize it with a serial object. And now it's, so at runtime, the object type of a P box that's pointed to is a pointer is at this point is a carton, pointer to carton. So the pointer to carton is dynamic type, and that is something that cannot be determined at a compile time. So essentially, you could be changing the value of this pointer P box during the execution of your program. And so the compiler really doesn't really deduce what this could be and until your program actually runs, and then that type of the object can be determined. That's the dynamic type. Dynamic in the sense that this is the type that's determined during a runtime. Okay, so so this example here we use pointers. So the same. Just remember in this particular chapter, when we talk about, we're going to use an example mostly with the pointers, but the same reasoning is the same thing with the references. So, and what do we get for a polymorphic behavior? Polymorphic behavior is that you have to have virtual functions. And over here, we're talking about the objects, how you can use a pointer to resolve an object type dynamically. And you're able to hold onto an object of a derived class in a pointer that's pointing to, as declared, a static type pointing to a base class. So, and that is fine. But then to really get the polymorphic behavior, you got to have this dynamic binding. And what's dynamic binding? So take a look at this hierarchy here. We got a box base class, and I have a bunch of derived class from box. Now you got a carton, you have tough pack, and other box. So now let's say we have a statement here, and we want to invoke that volume. And now here, this volume function, member function of a box, is declared as a virtual. And what that does is that this virtual function, when you invoke this with the box pointer, at a runtime, the actual object could be a carton object, could be a top pack, could be other box. And that the dynamic type of that pointer to box is resolved at runtime. And the function call for volume is not necessarily box. If it's resolved to a carton object, then actually it's going to be invoking the volume function in carton. And in fact, this volume function here is set to be overriding the volume function in the box, in the base class. And this virtual specifier here allows the derived classes to overwrite that function. Override function basically with its own implementation. This box may have provided its own implementation, but then for specific types of boxes, and then the volume may be different the way it's calculated. And and so this is essentially, the idea of a polymorphism. You are going to just invoke this function that's on a base class pointer. And at runtime, the actual object could be one of those derived objects. And then the specific, the overridden function for the derived class is the one that will be invoked, depending on what this actual object is pointed to by box, okay? And then the opposite of this non-virtual member function, the regular ones that we have seen so far without a virtual keyword, this is essentially resolved statically in the sense that the compiler is able to figure out what function. Well, of course, in that case, the function is always going to be the one defined in that particular class. Imagine if they didn't have the virtual here, this is not a virtual function. And then this is simply just invoking the volume function of a box. It will not give you the polymorphic behavior. That's just the regular function call for that object, okay? So that is the resolution of this function. It's going to pick the one in that class where it's defined. And that's the static binding in the sense that when you have a function call, it's trying to find out what is the definition of that function. And that's the code binding process. It could be static in the sense that the compiler can figure it out during compile time. And then, or versus the dynamic binding, which is the actual function is determined at runtime. How is that done, by the way? So here's an idea. It's called a virtual table, or more commonly known as a V-table. So the V-table is an additional data structure that's maintained for a class object. If you have a class that actually has a virtual function, in this case, like for example, box. And because it has a virtual function, the compiler is going to insert an additional data member. Okay, so you declare your own, member variables, right? But the compiler is going to insert another one that's actually a pointer that will point to an array of virtual function pointers. And this, an array of a virtual function table, this is function pointers. It's in a so-called V table that every of those pointers um, basically point to the definition of the member function for that particular virtual function. So what does this what does this mean? Let's say so you have this object, you're trying to invoke a do more, and let's say do more is a virtual function. So at a runtime, this pointer to object, whatever the type is, and that type, let's say, is of course, it's a polymorphic type in the sense that it has a virtual function, and this is a virtual function. So at a runtime, this could be resolved to many different objects that in that class hierarchy, right? So when you invoke this member function on an object in that situation, the compiler is going to actually go through this special pointer, which is hidden. Of course, you cannot really use this in your own code, but it's going to be there if you use a size of, and they will see the size is going to be a little bit bigger than the class object has no virtual function, and that's assuming everything is the same. So it's going to use that hidden pointer to the V table to resolve that do more function. The do more actually is going to be here. Let's say it's going to be using this pointer and then +2, right? Advancing, it's just figuring out, thinking this array of pointers, and figure out this element. That's the one, to get to the definition of do more. And that's really how it's done. And this class, this object, the actual object that resolved at runtime, whatever that end up being, one of those derived objects, right? And it's, of course, for the polymorphic behavior, this needs to be a base class pointer. And so that then you will always use whatever that pointer to the V table associated with that particular specific derived class, and to find out the definition of that member variable. Okay, so that's really the idea how this polymorphism is achieved. All right. And then there's two more specifiers that's worth mentioning. These actually are not keywords because it kind of came in late. It was added on to into the language, and they wanted to preserve backwards compatibility, so they are contextual. When they are used in a member function declaration, and then actually in the context of or in even on the class name, we'll see there's what are the things, what other situations you may use this. And the thing is with override and final, these are basically they call specifiers, not really keywords, but really a technical difference. You don't have to worry too much. And I would say if it's a word that the language actually use that has a special meaning, even though technically you could use these words in other contexts to, for your variables or function names if you want, but obviously you're advised not to really use them. It causes confusion, right? So always add override specifier to a virtual function override. Now, a virtual function override in the case where we're talking about here, like a volume, and then this is overridden in these derived classes, right? The carton, tough pack, other box, they actually override this volume from the base. And so in this case, you should always add override specifier, which is added on to the end of the function signature. This is not part of the function signature, by the way. Part of the function signature ends with what we learned so far is the const, right? It could be a const member function, right? Which means it will not modify the current object. And that is the signature, but the override is not part of the signature. But this is really a nice feature here. When you add this override specifier to your function signature, in the context of a class definition, that it will actually allow the compiler to verify, is this function that you tend to override actually a virtual function from a base, either directed base or indirected base. If that's not the case, it's going to issue an error, and which is a nice thing. So that's because your intention is to be able to override. So then, this is just another nice feature for to prevent accidental errors. And so it's just you should just always add it. And then the final, what does final really? Final, actually, the word is very straightforward. Means that's final. Final, really. Okay. In the case of overriding, if you have a function override like the volume function, right, and then say up to this, now you're you're deriving from a base class, and you mark that function now final. Again, you add this keyword, not this keyword, just this specifier to the end of that function declaration. And now that means if there's another class that wants to derive from this class, they can no longer basically override this function that you marked as final. So that's kind of end of the line, right? And there are reasons for this, and especially with the library design, and if you're intending for making a library for people to use, there's a very good reason for using those final specifiers. Of course, in your exercises or some of the examples that you're going to see, that's going to be not going to be used often, right? This is again is one of the language features that it will. There are occasions where you're going to find that very good to use, but you're not going to see this very often. And then you can also have final classes. That means like the whole class is final, and that means you cannot derive from that class. That class cannot be used as a base class in a inheritance hierarchy, for example, right? And there's also a good reason for this. Depending on the specific problem you're trying to solve, and we may not see a whole lot of example about this, but just be aware this is there. And or if you read somebody else's code, and when you see this, you know what this means. And you can declare virtual functions as a private. Well, you think, well, how that's weird. How is that going to work? How do you override it if that function is a private? And then previously we said, well, private functions are always private. That's true, and they're still private, right? The private or not, that's the accessibility, and just the way it's designed that the overrideability, or like whether you can override a virtual function, they are orthogonal, they're unrelated. So regardless whether the function is declared as private or not, if that function is virtual, you can still override it. Of course, you can upgrade the accessibility. It's going to remain private to your current derived class, right? But that is really it's interesting, but also kind of makes sense. And because we're going to see a particular design pattern a little bit later that will kind of show you a good reason where this might be used. Okay, so just know that virtual functions can be private, and that you can still override it. And of course, you cannot really modify the accessibility in that case. And one thing that maybe I did not mention is, if you override a virtual function, you don't have to declare this override as a virtual again. Whether you use that virtual specifier, which goes to the beginning of the function declaration, or not, it's irrelevant. It's going to be always considered a virtual because you're overriding a virtual function, so this will be virtual. whether you use that word or not in your derived class. So it's just kind of a, and of course, whether you're going to keep using that virtue in a derived class when you're overriding it, that's kind of a matter of a taste, but it's unnecessary. So the authors of the book are of the opinion that there's no need to use that. Okay, but you, of course, you can, but it doesn't really make any difference. And the next point is in dynamic binding. Okay, when we talk about default parameters, of course, the virtual function could also have default parameters. There are still functions, right? And the default parameters. So the way that works in a dynamic binding situation, we know what dynamic binding is, right? You use a, let's say, a base class pointer, then you use polymorphism. You get different behavior at runtime. And that, when you use that, the default parameters of the base class apply. That means if you override a virtual function and then you now the base class virtual function has some default parameters, and then your overrides also declare some default parameters, just know that they're not going to be used. They're useless, right? That's kind of how this works. And um, so let's take a look at just kind of what we just talked about in the form of an example here. So in this class hierarchy, we have a base class box that's derived by carton and toughpack. And carton is derived further by crate and big, packet. And then you have toughpack that's, there's more specific toughpack. So you have big pack and tiny pack in terms of the sizes. So typically what you have is you have, let's say in the case of a carton, you override the volume. But then you also may add your own virtual function that you want your derived classes to override. That, let's say we call this do that. And then in the case of toughpack, it may add an additional override, additional virtual function, maybe do this, right? Something different. So, so the point is you can override the virtual functions from in the base class, from your base class, but then you can also add your own virtual functions that then, because this function, this class could be used as a base class of other classes. And so that's kind of a more sort of a common thing that you're going to see also. So that's really what this looks like. Now let's talk about virtual destructors. What do I mean by that, right? So if a class has at least one virtual member function, for example, the box that we saw that has a virtual function volume, and then you really should make the destructor virtual as well. For example, you say, virtual the destructor and let the compiler generate the default. So that virtual destructor, that is important because when you destroy, let's say the base, let's say you have, you want to destroy the object through the base class pointer. If your destructor is not virtual, then you could have just destroyed the base class object, but not the derived object that may have additional member variables, right? So by declaring this destructor virtual, then you're allowing the polymorphism to work on the destructors as well, so that the objects along the hierarchy are getting destroyed accordingly. So remember that analogy I used to peel the onion. So when you destruct, you're peeling the onion from the outmost to the innermost. Outmost means most derived, innermost is the most base. So you want to, because enable that feature when you're getting polymorphic behavior to your mode, there's a volume function on a base class pointer, like a pointer to a box. When you want to destroy the object through that base class pointer, you just have to have this virtual destructor in order for this to work. So this is important. So it would be a good habit to do. Otherwise, you may get surprises in your program. And since we have class hierarchy, now we got dynamic binding. Here's the thing: when you write a program, you're gonna encounter, okay, you may have to use different types. You have to be able to cast within the whole cast hierarchy. So there's this so-called upcasting, downcasting, crosscasting issues. So what do I mean by this, right? So remember this whole class diagram, or the quasi-class diagram that shown in the books, that has its own format, which is not the UML, but it's pretty intuitive, right? But still, you have a base class at the top, and then you have derived at the bottom. Just by looking at, remember that kind of hierarchy, this is how we usually pretty much always draw a class hierarchy that way, like the tree data structure. And so with that in mind, then you kind of know what up and down means. So in this case, let's say we have a pointer to a zero pack, which is the most derived. Now the awning, right? Remember the awning, this is the outmost layer. You got the box in the innermost layer, and that's really the most base object here. And so if you actually got a pointer to the zero pack object here, now you can cast this to its direct base, which is a carton, right? No problem. It's that's easy, and then this cast can be done, actually statically. This is called upcasting. Although we're not drawing the tree structure, but you just you're thinking of this awning versus that tree. The box is at the very top. So upcasting is totally natural and legal. Okay. Because look, you've got an object of zero pack, then it also means you have a sub-object of a carton and subject object of a box, casting to the upward. You have all the information you need for those objects to operate. Okay, so that's why, and of course you can. So here, this is you get into, of course you can actually point to the most base object, the box. And so that assignment works. and then the other situation, right? Let's take a look at this. What about the other way around? So if we got a base class pointer here, you have a box pointing to a box, and which is obviously the base class. And so you initialize it with a carton, right? Fine. This is a derived object. Now, so because we know this is actually a carton object, right? And you can, of course, static cast that box pointer back to pointer to carton. That's no problem, because that's what the object is in actuality, right? So that's fine, because you have all the information about carton object. And then remember that hierarchy, we also have a zero pack that derives from a carton. Now, can you cast box to a zero pack? Right? So all you've got so far for this object is a carton. You have no information about the specific data members, or the member variables have a zero pack that's unique to zero pack. You don't have another layer here for zero pack. You can't not really cast that to a zero pack. It just doesn't work. The behavior is undefined, well, which usually means your program could crash, and of course you don't want to do that. So, yeah, but also know though, here's the thing. The value of a box could change at runtime, and it could be assigned actually a zero pack object too. right? In that case, it might work, but then the problem is here you're using a static cast. Now, remember, static cast is compile time operator. At the compile time, the compiler can figure out the types based on the expression and how you declare those variables, right? It will, and then that will not be allowed. At least in this case, it will not be allowed. This is, the compiler does not see it statically during the compile time. So this is where a new operator is needed, and that's called dynamic cast. And so now let's say we actually initialize a box with let's say a serial pack. Okay. Now the serial pack is, or in the case if we continue from the previous example, let's say we assign that box pointer a new object, which is a serial pack. That static cast is not going to work still because this is a dynamic runtime information as far as what the object is going to be. Unless you run the program, the compiler will not evaluate those statements, right? And so it cannot figure out statically, but then you can try to cast it still. Well, in the case, let's say you use dynamic cast, you want to cast that box to a sort of a downward casting. See, from you got to hold on to a pointer to a base class, and now you want to cast that object to a derived class, right? That's called downward downcasting, and downcasting is how you're gonna. Is this okay? And then, yeah, you can use dynamic cast, but is this guaranteed to work? Not necessarily, because at runtime, this box may or may not hold a object that's compatible with the carton, right? If it's just simply a box instead of a carton, then of course that casting is not going to succeed. So in the case where it does not succeed, it will just give you a null pointer. The result of that dynamic cast will be evaluate to a null pointer. And then you, of course, just means in your program, you got to check for that, right? That's, the actual object type, the dynamic type at runtime. And, the dynamic casting may or may not succeed. Okay, so you have to check for the null pointer situation, because that dynamic type is, let's say, it just cannot be casted to a carton because it doesn't have all the information for a carton object to work. Either it's carton object itself or another derived object that contains carton as a sub-object. In that, if otherwise it will not work, right? But the dynamic cast operator will allow you to operate in that situation. Okay, so there's the thing about, can you use polymorphism inside a constructor? Let's say you have a base class. And during the initialization of the object, you're constructing the object in this constructor. You want to do some initialization. You want to call foo with a value of 42, and you want to call bar member functions. And these are the virtual functions, by the way. And that means, well, we were thinking we want to get polymorphic behavior. Somehow want to construct a base object with sort of a derived member overridden function behavior. That cannot be done. It cannot be done. It's not allowed. Well, what end up happening is, well, for kind of just think about this intuitively. The object, remember the construction process from top to bottom, or thinking of the onion from the innermost to the outermost. We're constructing the base object. We don't really have any information about the derived object yet. How can you expect these functions to call, the overridden version from the derived class? It doesn't make sense. So that's why it doesn't work that way. And what a compiler is going to do is it simply will be using static binding for these situations, even though they are virtual functions. That means it's going to call its own version of a function definition inside the base class, not the polymorphic version of it at runtime. Okay, so you need to be aware of that. Now, what if you really want to do something like this? you want to get the polymorphic behavior. How do you do it? So that's the idea, is this dynamic binding during initialization EDM. And there's a solution, of course. Actually, the solutions are very simple. You basically create another member function called, let's typically call it, just call it init. The reason it's called EDM, and that's because essentially that's the pattern that people go for, and so people understand. Same language. So you have this init function, and this init function, by the way, the self may or may not be virtual. It depends on what you need. Then inside the init function, by the way, this is a regular member function. This is not the constructor, right? So in here, then we're going to call foo and a bar. These are the virtual functions that are actually could be overridden by derived class. Right here, it does override those two methods, two functions. So in this case, you get in the polymorphic behavior because now the object has been constructed. It does have all the information about the derived object. So then you are getting the dynamic binding in this regular member function here. Okay. So, so you see, we just moved the logic in the base where you do want a dynamic binding outside to a regular function. And so then, okay, that's not the whole story though. Now, since this is a separate, that also means that when you use this object, when you construct it, you need to just, you do the regular construction, but then you also need to invoke this init right after, okay? So that's really the way to do it. Now, there's a couple more things when it comes to virtual functions. You can declare a virtual function as a pure. Pure means it does not have a definition. And sometimes in the base class that you don't necessarily want to define that particular virtual function. You leave it to the derived classes because there's just no sensible implementation for, pretty much just the default implementation of that particular function. That is happening pretty often, by the way. In that case, you declare that function as a pure virtual function, and by using this syntax equal to 0. Don't confuse this with mathematical or assignment. It's not an assignment. Okay, it's a special syntax, like how you should do a equal to, like, default or equal to delete, right? Let the compiler to generate it, or delete the compiler generated one. And this is essentially just saying this is a pure virtual function with a no definition. And the compiler, when it sees this, it will not expect to process the definition. It has no definition. And when your class, in this case, if it contains a pure virtual function, as long as you can at least one of them, and then your class is considered or called an abstract class, that means it's incomplete. Okay, the class is not complete because now you have no definition for that virtual function, right? So you cannot instantiate an instance of that class, or you cannot construct an object of that class. It's considered abstract. And then you would have to have a concrete class where you do define, override this virtual function and have a definition for that function. And then you can create an object of that. So the abstract classes, well, there's a lot of usage of this, right? In the case of designing, especially when we talk about design patterns, and we'll look at a particular design pattern shortly. And there's another special case where your function, your class consists only of pure virtual functions, or with the exception of a virtual destructor, which is generated by the compiler. In this case, what you see here, this will be considered an interface, right? It's still an abstract class, of course, but this also can be called an interface. And this has basically no definition of anything. And it contains a bunch of pure virtual functions. And this is, and then of course, and then you through this, you get in the polymorphic behavior, and what the polymorphism works through this, let's say a pointer to vessel in this case. but then this provides no default implementation of any of the virtual functions. So again, the interface also has its user quite common as well, and that would be interface. And we're gonna actually take a look at an example here with this vessel idea, right? So vessel is an interface. It contains a volume, a pure virtual function here. And then you got a bunch of classes here that derive from it, and they override that volume and provide a definition for can and a box. And then the box may also have a coordinate top pack that that provide further custom behavior for volume, how the volume is calculated. So in terms of code, we're going to take a look at this, for example. Let's say we actually have those classes defined, and we just create some sample objects of those types. And then we can put them all into a vector, for example, and using this common base class pointer, pointer to vessel. And so this can hold on to obviously all those objects. And then perhaps we're gonna basically and then look through and then just run this volume function and through this pointer to vessel. Now we know the static type is pointing to vessel, but through polymorphism and dynamic binding, this is going to invoke the volume function of those respective overrides, right? So that's really kind of an idea how this works. And I think to point out, I previously mentioned, okay, don't use raw pointers, and because they have to deal with the allocation stuff. Well, so in this case, you do know that your pointer is pointing to those uh, automatic variables, and those objects will be deallocated, right? They will be deallocated at the end of the function call. And so this is fine. As you see, this is why you do not see a delete. Okay, why don't we delete the pointers? And the memory hold on to those objects will be reclaimed, right? They will be basically destroyed at the end of the function call. And so that's okay, right? So I mentioned there's design pattern that the book also kind of mentioned about this, and they say it's kind of a outside the scope of the book. And but then from time to time, I do want to bring in a couple of design pattern to the lecture. And so one of the really common, so first of all, what is design pattern? And design pattern really simply is just in OOP, when you do object-oriented programming, and there are common techniques that you will find yourself employing quite often to solve certain kind of problems. And those sort of ways of structuring your classes or objects um, become so apparent once you know some of those design patterns that you're going to want to employ them because they're tried and true stuff. Like, well, we'll talk a lot about idioms, a bunch of idioms in C++, how you program in C++. That's C++ language specific idioms, but when it comes to OOP, regardless of what language you use, there's many common patterns. There's a couple, maybe a few dozens of them that the community has come up with, and now everybody just know if you want to become a good programmer, you're going to study and learn them, and that becomes part of the common language when you communicate with other programmers. And they are really commonly used in almost every library you use. You're gonna it's safe to assume that you're gonna see some design patterns in that library design, including the standard library we're gonna see shortly. Let's kind of introduce what this template method is. So the intent of this particular design pattern, and by the way, this is the definition from the classical book called Design Patterns, written by so-called the Gang of Four. Okay, it's an old book written in 1995, but see the design patterns discussed in that book, they are they are still very much valid. I mean, like so many years later, they're still okay. But then there's more patterns out there, but those things that's discussed, a couple of dozen there, they're still very much alive and used in many places. So including this, the template method. Now, what template method is, it defines the skeleton of an algorithm in an operation. And it defers some steps to the subclasses or derived classes. It lets the subclasses redefine certain steps of an algorithm without changing the algorithm structure, which is kind of, we're talking about a template, how you might want to implement an algorithm. There's a template here, and there's a couple of points where you can customize through derivation, right? So perhaps a little more clear with a picture here, with a diagram. So you have an abstract class, and then you may have a template method, and this may be a regular non-virtual method. It depends on what you need to say. It's not really customizable because this is the whole point of this class. It provides a template of a particular algorithm, but there are ways you can customize it, and it's intended to be customized. So you may have a couple of steps, and then in terms of this template method is, let's say the template method is like this. You execute step 1, and then you check some condition of step 2, and then do a step 3, and then otherwise you do step 4. So, and perhaps step 1 and step 2, they are mandatory. You have to override them. And then, well, actually, sorry, the step 1, step 2, maybe you don't need to override them. In the case here, the way it's defined, the italics here means that they are pure virtual. And then here, these are basically, there's a default implementation here, right? And so, as you see, it gives you the places where you can customize. If you some of the methods, some of the steps you don't need to customize if that suits your needs. And so then you have a concrete classes that derive from this abstract class. It's really designed to be used this way, and you really, of course, you cannot instantiate a sub abstract class, right? So we just learned that because it's incomplete, and there are some functions that are that are pure virtual. There's no definitions, of course. And then you have concrete classes 1 and 2 here, and then the concrete class 1 that will override step 3 and step 4. So we provide our custom behavior for this particular concrete class, and we're going to use the default implementation of step 1 and 2, right? See this? And step concrete class 2, and a different scenario, a different kind of implementation, and here we're overriding everything. Okay, so we're just going to take advantage of all these customization points. Okay. So this is really kind of the basic idea behind the template method. And this is a pattern that's used very often, especially, for example, maybe when you're coding, you start off with, let's say this is what you have, concrete class 2, you have the whole algorithm inside, this is what you started with. And then later on, you find out, oh, there's another thing you want to add that's very much similar. There's just a couple of little tiny little differences. What do? You can refactor that class that had everything or the whole algorithm. And because there's a commonality, you want to factor that out into an abstract class and using the template method to, now you design this template method that's the commonality between the existing class and the new class you want to add. And they bring up this structure here, and then it allows you to, you're not changing the behavior of concrete class 2. The consumers of concrete class 2 continue to work as is. But now you also allow a new alternative implementation of that class that shares a bunch of code. You're not duplicating code that was present here. Now there's some minor differences. So then, and this is kind of the idea here. You're trying to factor out the common parts, and this is sort of a typical thing to do. Okay. So a typical, then let's take a little more concrete scenario. And there's many examples. So this is just one scenario that's described in that book. So let's say you have an application abstract class. You have a document abstract class. This is like about document editing. And the application abstract class defines a couple of functions. Essentially has a some template methods. Maybe the template is about how to add a document and how to open a document, and it provides you customization points with those virtual functions here, and do create document, right? Um, and or can you open a document or about to open document, which is like a hook. And this provides you a point where it notifies you right before it opens the document, and then you may do additional things right then. And this operates on a document. This document cooperates with this, and you see this association. This is the type, the relationship that we discussed before. This is the, if you recall, right? This is the so remember, there's a composition. There is what's the other one? Um, com, a kind of blanking on the name now. So essentially, it's this is associated with application, and let's take a hold on. Let's take a quick look. Let's take a look at class diagram. Yeah. So the okay, all right. Aggregation. Sorry about that. Is the aggregation. Remember this hollowed or empty diamond here. This is the aggregate, and this is the aggregation relationship here. And then this basically can maybe hold a member variable to a document, maybe a bunch of documents. I see the docs here, maybe a vector of them, and it maintains sort of the pointers to them, to the documents objects. And because, of course, a document can exist without application, basically the application is not responsible for maintaining the life cycle of a document objects. Okay, so this is a basically aggregation, and then instead of the composition, so aggregation relationship here. And by the way, this is not a pure exactly a UML diagram. This came out so early and before UML came along, but you do see elements of a similarity, and that was adopted into the UML standard. And so it's this triangle shape of arrow here, and it's drawn here in the middle, but in the standard is going to be at the very end. This is the inheritance hierarchy, right? So this you got a my document. These are the abstract classes, and now you got concrete classes, my document, and then you basically customize. You say to do read for this type of document. This is how I want to read. Yeah, so this do read is italics font here, and this allows you to customize and to define. You actually have to define, in this case, the intention here. This is more pure virtual function here. And then you basically customize, and this is what you want to do with your concrete document class that derives from this abstract class. Same thing with the application. So you have a customization points that you want to deal with your specific application. And this application maybe deal with my document. Maybe it deals with other documents too, but at least my document. So it has this dotted line arrow. And dotted arrow here, it kind of indicates a dependency. This is also kind of adopted into the UML standard. It's a dependency of my application class, because this is going to actually create my document objects from my application here. All right. So this is sort of a more of a concrete scenario here. So let's summarize. Polymorphism involves calling a virtual member function of a class through a pointer or reference. Remember this base class pointer, also or reference. So what we're talking about when we talk about pointers and the references similarly apply. We just choose this. Of course, this is one type of objects. This gives the because if you do a regular object, you're not getting the polymorphism because there's no room for the compiler to figure out to have that point. There's not an address of some object which could be one of those derived objects, right? So and then a virtual function of a base class remains virtual in its derived class. I didn't mention this, so essentially you don't have to use that virtual word. keyword here in the derived classes anymore. They're going to be always considered virtual, whether you use it or not. It does not make sense, or it does not make any difference. The destructor of a base class should be virtual. It's just a good habit. You should always do it. There may be some exceptional cases where you're dealing with a specific type of destruction of an object, and then maybe you have it. But then again, most of the time, you do want to just declare this as a virtual. That will take care of the case where you want to delete objects through the base class pointer. Function overrides in a derived class should use the override specifier. And this is again just to avoid unintended behavior, because let's say you modify the base class. Once you have, let's say you have a bunch of derived classes that overrides a certain function in the base class, and then somehow somebody modified that function signature a little bit, maybe from a const to non-const now, whatever that change might be. And then if your derived classes don't have the override specifier, then the compiler is not going to complain. It's not going to inform you, and so you're going to maybe get into a weird behavior that you don't know what's happened. But then if you use that specifier, the compiler will tell you, okay, well, you intend to override something, but that something is no longer there because that signature has been modified in the base class. So function overrides or classes, they can be declared as a final. To basically then you can no longer derive from that class or to override that function again. They are final. And default parameters in the virtual functions are assigned statically, right? So there's no dynamic binding in that situation. That's just kind of how that's designed. It kind of also makes sense. And dynamic cast operator can cast from a pointer to a polymorphic base class to a pointer to a derived class. That's called a downcasting. Okay. A pure virtual function has no definition. All right. A class with at least one pure virtual function is an abstract class. So you cannot construct an object out of an abstract class. Abstract class has incomplete definition because at least one of the virtual function definition is missing, and they are pure, right? So no definition there. So if a class has only pure virtual functions, then it's called an interface. So it's still also abstract class, but you can appropriately call it interface. Okay, so that's that. Pretty much that's what I wanted to share about this chapter. Thank you.